This time, let's try another method. This will be probabilistic in nature, and it rests on the following observation. That instead of trying out all 6 strata of the Grassmannian, we should say that, well, okay, the first strata was an open, Zariski open subset of the Grassmannian, and therefore the probability that some of the lines will lie inside of the complement of this first strata is essentially 0. And what we can do is, if we could take a random polynomial, then all lines probably will be on the first strata. And if you don't give me a random polynomial, then what I can do is to randomize the coordinates. So that means I will apply a random linear transformation to my projective space and apply this to my polynomial f. And then this essentially randomizes the position of the lines, so that now I expect to be able to capture all lines using just one of the strata. Let's see how this works in practice. So now I'm defining a matrix. I want it to be a 4x4 matrix. And I will just randomly take integers between -10 and 10. And I need 16 of these things. Okay, so this is a notation that I haven't shown before. Previously, I used to write a sequence of sequences. Instead, you can write a single sequence of entries, provided you specify the shape with these first 2 numbers. And this creates a matrix. It's 4x4 with random entries. Let's see what it looks like. Okay, so this is the random matrix we have. Since I want a linear but invertible operator on P3, let's just check that its determinant is non-zero. Sounds good. Now here's what I'm going to do. I'm going to apply the row vector x, y, z, w to M. R was our polynomial ring with variables x, y, z, w. I'm changing this matrix M to have coefficients in R. That doesn't change my matrix, but it satisfies magma, so that I can now compute this product. Let's see what that looks like. Okay, now I have 4 linear functions. So this is the first one, second one, third one, and so on. And I want to use these 4 linear coordinates to transform any given polynomial f, essentially randomize it. So f was this f here. It has this strange shape. It has few monomials. And now once I apply this random transformation of linear coordinates, f will have many monomials. And therefore I expect the first strata to capture all lines. So I want to call this matrix linear change. But in fact, let's take the elements in this 1x4 matrix. So linear changes now consist of 4 elements, each of linear in x and y. Okay, now evaluate f on this coordinates. Now I've substituted for x this linear expression, for y this linear expression, and so on. This operation is invertible, and therefore I have not changed my surface. I have not changed the geometry of my surface. So the surface defined by f. Now you'll see that the lines inside of this thing will lie in the first chart of the Grassmannian. And here it is. We see now that there are 27 lines on the first strata of the Grassmannian inside our new f, the transformed f. There happens to be 2 lines that are in fact defined over Q, and the scheme defining these points is reduced. So that's what we were checking here. Okay, so this shows that we didn't need the second strata if we do this randomization, but it takes a split second longer. For polynomials of higher degree, it might take much longer. So then you have to take smaller matrices. So this is relatively large and maybe unnecessary. You can take a smaller matrix, but then the probability that you get the generic thing is lower. So you would have to do more tries. So here on my first try, I get a surface where all lines on the first strata. And this is why this operation would be called Monte Carlo. Usually you would loop over many of these linear transformations and see how many lines there are. So let's do that too. So let's just get the number of lines and then output it. Maybe I say print here, and I want to put this in a loop, and I will want to skip this if the determinant is 0. Okay, what I did was to loop over randomly generating matrices to skip matrix generation if I happen to have determinant 0. In fact, I'm having about 10 attempts here. Maybe I should increment an attempt only if I manage to get a matrix with non-zero determinant. And then I change the coordinates of f, I count the number of lines, and then I print this count. So first thing is that when I executed this, I already had one example where there were 26 lines on the first chart. Therefore, this already reminds you that this probabilistic thing is not for sure true, so that sometimes you will not get the right numbers if you apply this probabilistic method. That's why you need to try a few. And then one thing we can try is to say, maybe this 10 by 10 matrix is too big. Let's see what happens if we take small matrices with entries between -1 and 1. Okay, so we now see these 26 more often. I think that's to be expected, but it was much faster, and this is a little bit surprising because my m's are in fact much smaller. So this is an example where you don't have to do the truly random thing. Sometimes just a little bit of randomness is enough. And computationally, this can be a huge advantage to introduce just a little bit of randomness. While we're at it, I just wrote a function that does this randomization business. And one thing I can do is to control the randomness size. Maybe I say size here and then go from minus size to size. And then I could have used this new function to construct my loop. But let's keep this at the back of our minds right now and then not use it right now. Now let's do one last example. This time it's not something of degree 3, but something of degree 4, because we know already the number of lines on degree 3 surfaces should be 27. It was not quite exciting. But for quartics, it's known that the generic quartic will have no lines whatsoever, but some of them will have lines. And really the only way to decide is to check. So you need either good pen and paper or computer using skills. So this time I generated this f, and this is now a quartic. As you can see, the degrees of the monomials are degree 4. And it says there are 12 lines on the first strata. Let's see what happens on the second strata. There are 3 lines on the second strata, and then we don't know what happens next in the other stratas because I have not coded it for this lecture. One thing we can do is use the Monte Carlo method that we just described. Let's try that. So it was called line MC, and I just plug in f. You see that line MCF gave me the count 16, whereas previously there were 12 lines on one chart and 3 lines on another, so my 2 strata gave me only 15 lines as opposed to 16. And this is why you might want to do this randomization, just to make sure that even, of course, f was not randomly generated. I created it deliberately to break this count, but this is one good example why you want to check all charts or use some randomization method. In principle, we don't know if this is all counts, so maybe we do this loop again. Okay, so for this randomization, I added this matrix generation command here inside of my line MC function, where until this random matrix has determinant non-zero, I keep generating this matrix M and then check that this has determinant non-zero. And now what I can do is simply create the sequence where I loop over 1 through 10, but I don't use this number II. And then I just apply line MCF. And then the result here, it was relatively quick. It was almost always 16, and in one case I got 15. So this convinces me that there are 16 lines, although I'm doing a probabilistic argument. Now this is a bonus section on generating random polynomials satisfying certain properties. So this is extremely handy. You have to keep doing this in some setting or another. And here's one way to do it. If you don't know the notation, then it will take you a while to figure it out by yourself. So here's the key notation. So first of all, I just create P3. I take its coordinate ring. Of course, I could have just taken a polynomial ring in 4 variables. I choose my favorite degree. In this case, I want to generate a quartic. And then I take all degree 4 monomials in this polynomial ring R. So what I'm going to do is to generate a degree 4 polynomial satisfying some conditions. What I do is I enter into a loop with repeat. This loop will end when certain conditions are met. What I want to do is first generate a non-singular surface. So the f should define a smooth surface. So non-singular scheme proj RF does that. Of course, you should have your own command to make this check. And then I apply my lines on first strata function to f. So this f will be generated in the body of the loop. We'll get to that in a second. So lines on first strata f should be greater than 0. Lines on second strata should be greater than 0. So I do these 3 checks. If all of them are satisfied, then I exit the loop. And here's what I do, and this is the most important line. I say random subset, I say index set to set applied to mons, and then I say 5. So what this does is mons, remember, was the monomials of degree D in R, homogeneous monomials. This is unfortunately not a set, it's not a sequence, it's an indexed set, and random subset works with sets. So you have to use index set to set conversion. Now this is a set, and when you say random subset, you have to give an integer as well to take a subset of size 5. Again, feel free to stop the video and experiment with these functions to see what mons outputs, what index set to set mons outputs, and so on. And it takes a random subset of size 5 in monomials. So it gives me 5 monomials randomly, and I generate a random coefficient between -10 and 10 for each of the monomials in this random set. I sum them up. This is my polynomial with support on 5 monomials. I print it out and then perform this check. Let's try this out. You see we ran through many f's. The condition I wanted for small monomials wasn't so frequent, you see. But in the end, we found an f. That's the f. And we can check lines on first strata f, lines on second strata is 3. And let's also check what our Monte Carlo business does. So this is very surprising to me, but somehow there are 16 lines again in f. And that concludes our discussion for today. We've gone through many of the basics that you need to work with Magma. We've gone through basics about the fields of definition of points, to working with Grassmannians and finding lines and surfaces, to this extremely important generation function for polynomials. And typically what you're supposed to do is to write this thing once, put it into your startup file, and then you don't have to worry about it. So I have my own functions that does this, that are built in, but I did not use them for today. On Wednesday, we will study a different aspect of lines on surfaces with a slightly more transcendental element and a variational element, this time not on lines, but on the surfaces themselves. See you then.